The Indian Machine Tool Manufacturers Association, IMTMA, providing the cutting edge to India's machine tool industry. IMTMA was formed in 1946 with a vision of providing a one-stop impetus for the machine tool industry in India, spearheading India into the forefront of industrial revolution by providing a platform for symbiotic industry growth and innovation-led machine tool technologies. What's more, IMTMA has today become a center of excellence for focused application-based training.
Welcome everybody to the online training programs from IMTMA. A very quick overview about IMTMA. The full form of IMTMA is Indian Machine Tool Manufacturers Association. We were set up in the year 1946 as a machine tool member organization. Today we have close to 470 plus members, and we take up multiple activities which include government advocacy on behalf of the members. We conduct a number of corporate training programs. We organize the IMTEX Machine Tool Expo annually. And besides that, we conduct a lot of training programs where we are focused on enhancing the competitiveness in manufacturing. We have conducted over 126,000 plus man days of training so far, with a portfolio of 200 plus standard training programs, over 4,500 companies whom we have trained till date, and with a participation of over 32,000 professionals so far. Our technology center in Bangalore and the technology center in Pune, and each of these facilities are fully equipped with all the requisite machinery, metrology equipment, accessories, automation lab with robot, and is completely industry 4.0 ready. We deliver our training programs in 4 different ways: short-term programs, in-house programs, e-learning, and long-term courses meant for young graduate engineers. Our classroom training programs are delivered by experts who have experience in excess of 30 years, with a blend of theory and hands-on training wherever possible. We supplement the programs with demonstration of live machinery or industry visits wherever possible. And we encourage a healthy interaction between the participants and the faculty through the program. Our e-learning initiative is delivered through an exclusive e-learning portal, and the current portfolio is about 10 programs which can be accessed by the participants at their own flexibility during the license period. And the entire program can be taken at their own convenience and flexibility, with assessment, evaluation, and certification being provided through the e-learning platform itself. Ever since April 2020, we have come up with the online training initiative, and till date, we have completed over 300 programs, addressed over 15,000 participants, and we have made these programs easily accessible to various types of participants, which can be taken up at a minimum training budget. And we enable live instructor-led programs with interactive question and answer sessions, polling, chat box, and we also provide live demos wherever possible during these training programs. Long-term programs are primarily meant for young graduates who wish to improve their employability prospects by taking up a few programs on design, production, automation, FEA, and these programs are available in long-term mode for young engineers. We thank you. Please visit our website, imtmaelearn.in and imtmatraining.com. Speaker for the day is Mr. Srinivas. The program shall be delivered by Mr. Srinivas, who is a mechanical engineer by qualification, with a post-diploma in marketing and sales management, a diploma in statistical quality control, and he is also a Six Sigma black belt. He carries more than 25 years of experience handling technical engineering planning at Bosch, and has deep expertise in grinding technology. And in his professional career, He's been associated with Bosch for over 28 years, and which includes head of process planning. And later he was with UCAM Private Limited, Electronica Machine Tools, and XNG Automation. And currently he's a full-time trainer, providing various technical training programs. And assisting him will be Mr. Madhu. And Mr. Madhu has also been with Bosch for over 2 decades, and he has deep expertise in providing. He's been associated with the Bosch training center, vocational training center, and he has deep expertise in manufacturing planning, hydraulics, pneumatics, and jigs and fixtures. I welcome both of them, but the lead speaker will be Mr. Srinivas. Over to you, Mr. Srinivas.
And today's this 1 hour session, we will take you through the concepts of grinding and its industrial applications. And first, I will brief you about overview of grinding and the grinding machine and its types, grinding wheel selection, grinding wheel specification, introduction to grinding process. These things will cover. This will give one bird's eye view of grinding, but actually this will take about nearly 2 days session. This will, but here I am just in 1 hour. I am giving some bird's eye view of the grinding process, and also we'll cover here overview of grinding system. What are all the things included in a grinding machine, and dressing method and factor influence grinding, and some example of troubleshooting and productivity. Now let us start with grinding. So in any manufacturing setup, the grinding is a finishing process, which involves multiple parameters like work material with correct heat treatment, process parameters, and selection of right grinding wheels machine. So this grinding is a finishing operation. Here, this will come at the end. So initially raw material will come, and then the soft edge operation like turning and milling will happen. Then it will go for heat treatment, and then it comes for grinding. Here, the grinding is most critical operation of all this in the entire supply, this process chain. And here the grinding wheel plays a major role, and also machine requirements are also very stringent, and skill of the operator also matters. So since it's a final and critical operation, any rejection at this stage, it involves high cost and affects the productivity of the company. So the grinding technology program is designed with the intention to impart practical approach for grinding with appropriate industrial case studies. So our main intention is to give some examples so that the participants will understand the practical aspects of grinding. That is the main intention. As I told, this IMTMA, this is conducted for 2 days program. Here I am giving some bird's eye view of it. So the system approach for this grinding process, like what are all the system inputs? So one is, as I told, machine tool, that is structural compliance, kinematics of the machine, and what type of bearings used and spindles used. See, this is very, very, very critical in grinding. For example, if you are doing rough grinding, types of bearings used and spindles are different. If it is a fine grinding, it will be different. So depending upon the application, this machine is designed. Similarly, operational factors like grinding cycle, speed, feed, depth of cut, these things will come. This basically comes in the program. And work material. So what type of, it is configuration of the component. If it is some intermittent cut is there, you may be using different types of feeds and speeds. If it is a continuous round and profile, it is different one. So depending on the geometry of the material, you may have to alter the grinding parameters and surface properties. If it is very hard surface, or if it is very more stock is there, then you will be having different parameters. When it is a fine grinding, it's less stock. So that depending upon the work material, you may have to change the parameters. And material properties. Material properties means like hardness of the material and toughness of the material. And tooling and supplies, like abrasive, what type of abrasive you are using, coolant, and work holding. Work holding, you may be holding between center, or you may be holding with the check. So these things will come with respect to process. That is, one is machine, operational factor, work material, and tooling and supplies. This transforms in grind, then grinding will happen. Here, power, displacement, vibration, acoustic emission, force, temperature, these things will, and in process monitoring, those things happen in grinding. Actual grinding happens here. And finally, what is that we expect? We expect that is form error, that is roundness, straightness, and dimensional accuracy, and surface finish, and waviness, and integrity. So these things will the output of the grinding process. Now we'll come, what is grinding? So grinding is the most common of abrasive machining. In case of milling, what happens? The cutting tool that actually that our tool will cut the material, whereas in case of grinding, this abrasives, this is called grit. This will remove the material, and it is a material cutting process which engages an abrasive tool whose cutting elements are grain of material known as grit, and this is grit. Actually, these grits are embedded in this bonding material that I will come in detail about grinding wheel. And these along the periphery, there will be number of these type of grits will be there. So when wheel is rotating and work is rotating, it will come in contact with number of grits so that it will remove the material. And the grits are characterized by the sharp cutting point, high hot. The characteristics of this grits is high hot hardness and chemical stability and wear resistance. And grits are held together by a suitable bonding material and gives shape in abrasive tool. So this is grinding wheel. Okay. And now we'll come to how actually the interaction takes place. Whenever this grinding wheel rotates and when it crosses this component, the grinding takes place in three phases. One is cutting, where material removal process, it will remove the material, and then plowing. Next subsequent grinds will, displacement will happen. This is called plowing, displacement process, and then finally sliding will happen. Like this, in the three stages, the finishing of the component is achieved in grinding. See, in grinding, we achieved the accuracies 3 triangle and 4 triangle, that is less than 5 microns in rough grinding to the extent of 5 to 8 microns, and in finish grinding with less than 2 microns. Even in super finishing, we may the match grinding and all we will achieve within less than 1 micron tolerances. That is the accuracy we can achieve in grinding. So when we talk about 1 micron, see, for example, in turning, we can achieve at the about 6 to 8 microns, and in milling, vertical milling and horizontal milling, about 10 microns accuracies we can achieve. Whereas in grinding, we talk about less than 5 microns and less than 1 micron also in super finishing. So this is the accuracies that we are expecting. What is 1 micron here? Micron means what? 1 micron can be visualized like this. So if you take the diameter of this human hair, diameter of human hair is about 70 micron. If you vertically slit that into 70, that is 1 micron, or it is equivalent to 40. The naked eye visuality of threshold is 40 microns. You can visually see only 40 microns thing. And our human white blood cell is about 25 microns, and red blood cell is about 8 microns, and bacteria is around 2 microns. So this is the accuracies what we are talking about in grinding. So it is a precision process. And usually what is that we aim in grinding? One is surface finish, and second thing is straightness, form characteristics like straightness, roundness, and cylindricity. That is what we expect in grinding. It is a finishing process. So most of the time we aim for the stringent tolerances of form and surface finish. Then why grinding is required? See, we understood what is grinding and why this grind application, why grinding is required. So machining materials which are too hard for other manufacturing process. So once after heat treatment, hardness will be in the order of about 50 to 60 HRC. That you cannot do machining by turning or milling. So then you have to go for grinding. So machining of material which are too hard for other manufacturing process. Then we go for grinding. And grinding is finished for mating parts with minimum friction. That is, whenever, for example, the shaft and journal, these two, the mating parts are comes, then both the surfaces should be ground. Then only we will get the right fit and tolerance. And close dimensional accuracy, wherever we want close dimensional accuracy, then we have to go for grinding. And high degree of surface smoothness, surface finish, when we require, for example, these type of faces and ID, where we require very high surface finish, then we'll go for grinding. And achieving stringent form geometry like roundness, straightness, and cylindricity. These things, when very critical, this we can achieve only in grinding. Grinding or next super finishing process like honing. And for honing also, the grinding should be a pre-process. We have to grind and then we have to hone. And finishing of foils with relatively reliability, size, and form retention. We want consistent size requirement and also form retention. Form retention means if we achieve this roundness and straightness, the retention of that over a period when you are doing mass production, you should retain. Then we'll use grinding. And finishing components with intermittent cuts. Sometimes intermittent cuts will be there. At that time, if you are doing turning or milling, turning if you do, that tool itself will chip off possibility. But whereas in grinding, that will not happen. So these are all the places where we use grinding. So links in the grinding process. So what is that? One is material. What type of material we are grinding, whether it is hardened material or it is soft, or what is the hardness of that material, and what type of material we are grinding, whether it is diamond we are grinding or whether we are grinding aluminum or we are grinding steel. So it depends upon our process depends upon what type of material we are in. That is number one. And next is grinding fluid. What type of coolant we are using? For example, aluminum we are using different coolant. For steel we use different. If you are grinding diamond, then it will be a different. So here grinding fluid is another link. And next link is machine. What type of machine you are using? You may be using, you cannot use same machine for everything. So in most of the machines, by manipulating our cutting parameters and some certain tooling, we can use same machine for different material and different type of different configuration of the parts. And the next is grinding wheel. So grinding wheel, this I will explain in detail. What is the specification of the grinding wheel? That is also critical. And then comes clamping method. How you hold the component, different configuration. If the wall thickness is less, how you are holding, or if it is a rigid bar, how we are holding. There is method of holding. And then another next link is your what type of dresser you are using. Dressing is very, very critical in grinding. First, you have to prepare the wheel. That also I'll explain in detail. And then comes setting parameters. That is that program what we use, what type of feed, speed, cutting speeds we use in grinding. So these are all interlinked. Why I have shown like this is interlinked. See, for example, one of them is a problem also, you don't get the required quality. So these are all interlinked things. So as I explained, so machine condition like spindle rigidity, alignment, vibrations, and grinding wheel, if it is specification, grinding wheel is very, very critical. And wheel balancing is critical. When it comes to dresser, right specification and type of dresser, what you use. And process parameters, cutting speed, feed, depth, and dressing method. And coolant system, coolant pressure, temperature, coolant nozzle. And support elements like filtration unit, in-process gauging, and dynamic balancing. These are all the things which comes critical for grinding. This is the link I am just elaborated here. This is one pictorial view of the grinding machine. Here, this is the workpiece. It is held here. Work head, this is work head, tailstock, and in-process measurement. This is the in-process measurement, CR60. It's a momentic gauge. And this is coolant chilling unit. Many times when you are grinding the parts with accuracy less than 1 micron and all, the temperature of the coolant is very, very important. So cooling chilling unit and hydraulic power pack, this basically for power, this is for clamping mechanism, and coolant filtration system. This is also very, very critical, and dynamic balancing unit. And this is in-process gauge digital display, and this is my monitor. So this is the overview of our grinding machine. Okay, now we know so far we understood what is grinding and why grinding, where we are with grinding. Now we'll see applications of grinding. This grinding is very, very critical in auto ancillaries. In most of the auto components are ground, and in steel industry and bearing industry and electronic components and devices and aerospace. Aerospace, lot of applications are turbine and medical industries. So there are some examples of auto components like camshaft and this surface finish grinding, cylindrical grinding. These are all the things, applications where we use dry shaft auto components. Similarly, these aeronautical components, high precision, high efficiency grinding wheels. And aerospace industry is very, very critical, where we grind vanes, hangers, shrouds, panels, blades, honeycombs, etc. Shaft, etc. Such type of thing applications are there in aeronautical industry. And also in medical industries, like medical device shafts, spline shaft, and also in dentistry, you can see that the tooth is grinding, and they will use a very small tools here, carbide and diamond tools there. And in tool and cutter grinding, a lot of applications are there, like diamond wheels and silicon carbide wheels. In tooling industry, lot of applications like gear grinding and this gear thread cutting, such type of things are tools we use. And bearing industry. These are all some of the applications of grinding. So now, requirements of grinding process in today's competitive environment. What are all the main requirements of grinding technically and economically? Both we have to see. See here, whenever we need to achieve closer tolerances, as I already told about less than microns, like 5 microns or less than 1 micron, then we go for grinding. And that this is the challenge in grinding is low close tolerances and complex geometry. Complex geometry means whenever the component has got number of steps and also wall thickness is less, at that time it will be more critical. So complex of the geometry of the component is very critical. Consistency in part quality, complex geometry, consistency in part quality, and processing of new materials. Because some latest, like we have to grind glass or we have to grind carbide, different new challenges are coming nowadays. So this is also one challenge here in technical challenge in grinding, processing of new materials. And variety and volume. And also many times we for example, the ball bearing steel we are grinding, it is hard, but we may have to do in volumes. Then that wheel life is very, very critical. Every day you cannot change the wheel. So here that life of the wheel is very critical. So whenever volume is there, then when volume of material removal is more, then that wheel also should last long. So what type of wheel you select depending upon the material and volume of material removed is also critical. So these are all some of the technical challenges. And coming to economic thing, lowest cost per part we should always keep in mind. See, we may use high fund of wheel, but if its cost of the wheel is very high, then your cost per piece will go up. So that also you have to keep in mind. and flexibility to requirements of variable part geometry, and short production runs. And many times, places based on this, your the batch quantities will be less because you have to meet the requirements of different customers. So different components you may be loading to the machine. So short production runs also this should meet. So that is also one challenge in grinding. And short lead times. So there are different types of grinding machines, like some basic bench grinders are there. You must have seen in any industry, bench grinders are there. And then surface grinding machine. This is basically to create a flat surface. That is the surface grinding. And then cylindrical grinders. So this is usually used for our cylindrical parts like camshaft grinding or shaft grinding with stepped thing. And centerless grinders. And other special grinding machines are there, like super finishing machines, like lab grinding machines are there, and some tool and cutter grinding machines are there. These are all comes under the category of special grinders. So now we'll go in depth about grinding wheel. So this is the most important thing in any grinding machine. This grinding wheel is very, very critical. So what is the function of main grinding wheel? One is removal of stock, generation of cylindrical and flat cut surface, production of high finish surface. So, and cutting of operations and production of sharp edges and points. So this is the main purpose of this. So here, how this grinding wheel is constructed. Here, grinding wheel consisting of abrasive. These abrasives are embedded in this bond. And this each grids, I already explained, each grids and grids, these are embedded in this bond, and this has got high hardness. The grade of that is very important. Depending upon the material, we have to select the suitable grade. And structure. So how these bonds are distributed, how these abrasives are distributed in this bond is structure closely, or this I will explain in subsequent slides. See, this is the grain actually. This is the abrasive, and this is bond. This is bond. And this is grain size, and the grade of this is depending upon the type of material we are grinding. And structure is the distance, that is porosity, how much we leave between these grains. Okay. And usually this wheel is any grinding wheel. Grinding wheel specification is given like this. One is what type of abrasive you are using. Here, for example, 45C54H6S23. It means here you are using, if you are using aluminum oxide, then it will come A. If you are using silicon carbide, C. Okay. And if it is, if it is diamond, it will come D. So this is the type of abrasive. One is abrasive, and this is prefix. And here grain size. If it is coarse, then you lose coarse, medium, and fine, and very fine abrasive, depending upon the what type of how much stock you are removing, what type of material you are grinding. This grain size you have to select. Here it is 54. 54 means it comes into kind of medium size grain. And what is the grade? Grade is medium, soft, hard, and very hard. So here H we have selected. That means it is soft wheel. Similarly, structure. Structure, as I told, how grains are distributed within the wheel. If it is very close, dense, medium, or open. If, for example, you are grinding very, you are removing more material, volume of material, then you should go for open structure. If you are doing fine grinding, then you can go for dense structure. Here we have selected 6, that is the medium structure. And bond. What type of bond you are using to bond these grains within the base material? That is vitrified bond we use, silicate, shellac, rubber, resinoid, and oxychloride. And this is suffix, this is manufacturer's code. Okay, this will give you the overview of this grinding wheel specification. So this depends upon, one is material to be ground, what type of material. See, if you are grinding steel, you may use different type of abrasive. Or if you are grinding aluminum, then different type of abrasive you use. It depends upon the material to be ground. And stock removal, how much stock you are removing. If it is a finishing grinding, what type of stock it comes. And it is wet or dry. Sometimes we do dry grinding without any coolant. And speed and severity of operation and area of contact. So here, abrasive type, as I already told, this aluminum oxide is one, silicon carbide. If you are using aluminum oxide, say for this example, you can see here A60H15V. A is type of abrasive, that is aluminum oxide we have used here. Okay. And if you have got silicon carbide, then you'll use C here. And if you are using microcrystalline, then you use MC. And if you are using cubic boron, then you'll use CB here. And if you are using diamond, you use D here. So one is abrasive type. What type of abrasive you are using? That is number one. This is one. And next is this. This is grain size. What size of grain you are using? Grain size. For example, if it is here, we are using 60. That means 60 comes here. That is, it's a medium size. And it is fine size is also there, 100. For example, you are doing finishing operation, then you will go for finer grades. And if you are using rough grinding, then you go for like this, left side you will go 36, 24 and all that. And if you are doing super finishing operation like finish match grinding, you will use it 300 and 400 grades. Right? This is grain size, second one. And next, third is hardness, wheel grade. That's also hardness. And if it is here we are used medium, this one, that is H. And very soft, medium, hard, and very hard. If you are using soft material, then you will go for a harder wheel. And if you are doing soft, if you are using a very hard material, then you go for medium or softer grade wheel. And then wheel structure. Here also structure means that I told you how that if you open structure, we use it for when a high volume of material is removed, and finer structure when you are going for less volume of material is removed and finish. So this is structure. See here we have used 15. Is this structure here? This 15. And this last one is type of bond what you are using. Here vitrified bond is there or metal bond. Which type of bond you are using? So this is how this is the nomenclatures that we use for describe the grinding wheel specification. And in the latest development of grinding wheels, even other than that, we are using now new material like microcrystalline ceramic abrasives. In addition to this aluminum oxide or silicon carbide, now latest is this ceramic abrasive. Whenever you are the submicron particles and special sintering process, microstructuring, self-sharpening property. This has got self-sharpening properties. As you are grinding, it will microfracturing will happen and it will open, so that your dressing frequency you can optimize here. So instead of dressing once in 20 pieces, you can go for once in 100 pieces, because this will do self-dressing, self-opening type of thing. There we can use this ceramic abrasive. See, this is the comparison of a normal abrasive and the ceramic abrasive. Here what happens, there is possibility of this grain knocking out, tool breakout will happen. And here microfracturing will happen. Whenever you are grinding dressing, microfracture will happen in the grids. Whereas here it is macro and here it is microfracturing will happen. So that is the difference between wear pattern of your conventional wheel like aluminum oxide and silicon carbide, and this is the ceramic wheel. That is the latest in grinding wheel. So this works well in carbon, case hardening tool and high alloy steels. For the tool and cutters, like when we are grinding, we can use this Microflex tools. And this is one example. I'll just give one overview how one precision grinding machine looks. That's what I wanted to show you. I'll play one video. This will be So this is about just one example of one cylindrical grinding machine where we do entire operation, ID, OD, thread, everything in one clamping so that to achieve the better accuracy. That is the main intention. So now we understood what is the grinding machine, what are the different types of grinding machine, and what type of wheel we use, and what is the specification, how we have to define the specification of the grinding wheel, and what is the latest in grinding wheel like Microflex Tools. And in addition to that, new abrasives are also coming like super abrasive. We call it a super, it comes under a super abrasive wheel. One is diamond wheel. This is mainly grinding non-ferrous material, we use it, diamond, and CBN wheel, mainly grinding ferrous materials. And in this resin bond wheel, metal bond wheel, vitrified bond, and electroplated wheels. These type of other things, supervises. I will just take you through that. I will not go in there. And this is the thermal conductivity of different types. Like for example, diamond thermal conductivity is around 2000, and CBN is 1300, silicon carbide 67, aluminum oxide 33. This is basically a soft. This is very soft and this is very hard. Diamond is the hardest. And also the hardness, if you take it diamond, it is 90, and also this thermal conductivity, also the heat resistance capacity is also diamond is 2000 and hardness is 90, whereas CBN is 56. Silicon carbide is this is copper hardness 27 and aluminum oxide 50. This is only comparison. And this the vitrified CBN bond. What we have used is vitrified here. We use it for difficult to grind materials, tighter dimensional tolerance, improved quality, excellent metal removing capacity, cool cutting with some induced porosity. This we'll use it for mostly whenever tight tolerances are required, where life is. This is vitrified. This cost is high, and also high cutting speed is required in the machine, like 45 meters per second minimum is required. And also this is how to, similar to that conventional, here also what type of CBN you are using, grid size, hardness, structure, and bonding material concentration that you will show in this specification. Grid size, like how it varies, hardness, structure, concentration. This is specification of this super abrasives like vitrified bond will how. See, this is bonded vitrified. Concentration is 300. Speed is 40 meters per second. That is the requirement. Structure is 3. Hardness is P. Grid size is 91. And CBN type is 3B. That is the type of CBN you are using. This is how we specify the super abrasives. And vitrified application, whenever hardened steel is there, high alloy steel is there, greater than 60 HRC, stainless steel particularly, then you have to go for this vitrified bond CBN. Hard chrome, nitriding steel, tungsten carbide, and ceramic grinding. Then you have to go for this vitrified bond. Similarly, resin bond, whenever cut-off wheels are there, whenever groove grinding wheels and regulating wheels of the central grinding, such type of thing, we go for resin bonded applications. And metal bonded for profile start grinding, and in honing sticks, we are made of this metal bonded abrasives. And diamond, use it for this support stones in carbide glass. So diamond grade is best suited for grinding cemented carbides, glass, stone, granite, marble, concrete, etc. For that, we'll use abrasives. These are all super abrasives. And also monocrystalline diamond, MCD. This is for dressing. Dressers will be made out of this. These are all the different types of wheels we use here. This is a CBN wheel, examples of CBN wheel. Diamond and CBN internal grinding wheels. This is electroplated wheel. Electroplated wheels, here you did not dress frequently. This is the abrasives are deposited on this wheel, and this will long lasting life will be there, and there is no need of dressing the wheel in between. So your productivity you can increase in this, but stock removal will be relatively less in this electroplated. So this is one just consultation of all different types of abrasives and properties and material and application. For example, silicon carbide, very hard and friable, mainly used for cast iron. This one, the silicon carbides, and particularly for cutting off and snaggering with and like that, like aluminum oxide, hard and tough, and pink aluminum oxide, monocrystalline aluminum, ceramic aluminum, CBN. This is just one table. It tells what is the properties, materials, and application. And comparison of abrasives, different type of abrasives. White aluminum oxide. When we use white aluminum oxide, whenever dressability is good, and it has got this white aluminum oxide has got thin work pieces you have to grind, and very good surface finish you require, and dressability should be good. Then you'll use it, this one, aluminum oxide. When you go for ceramic, whenever tool life is very important, and dressability, surface finish, and metal removal rate is high, then you go for ceramic. CBN, whenever your tool life is very critical and metal removal rate should be high, thin work, then you go for CBN. And when you go for monocrystalline, the ceramic, what I told, whenever the dressing frequency is, if you want to have more, that means that optimum dressing and thin workpiece and very good surface finish. This is just consolidation of different types of abrasives and what type of applications you desire. And you know this how this cutting speed is calculated. V is pi dn by 1000 meters per second. And here wheel RPM is calculated Vc into 1000 by 60 by ds by pi. So here from this you can n is the RPM requirement, and then work RPM is Nw, that is given by Nw 1000 divided by pi, and speed ratio is given by Vc by Vw. These are all basics. One example I have shown here, that is RPM is given by, usually we use 30 meters per second, here Vc 30, and 1000 into 60 divided by, that is around 19 meters per second, 1900. So say RPM of this wheel should be around 2000 RPM. If you have got 2000 RPM, then you will get the speed of 30 meters per second. And the workpiece RPM, how to calculate? This is here Vw into 1000 by this, around 600 RPM. And ratio, speed ratio of that workpiece to this is wheel is 100. So this is just formula for calculating cutting speed and feeding grinding. That is the parameters. And also for different types of operations, like surface grinding, we usually use 20 to 35 meters per second. Thread grinding and camshaft grinding will go for 33 to 60. So this is about different types of operations, like surface grinding, external grinding, internal grinding. What is the type of tool we use, and what is the cutting speeds we use? That's the same thing we have to have. And then comes dressing. So in any grinding, we get the finish, whatever the requirement. It depends upon the how you will dress the wheel, grinding wheel. So here one is truing of the grinding wheel. Whenever you mount the wheel, first you will true it. Truing is a process which is done to make the job axis concentric to the machine axis. So whichever high points are there, that you will knock it off. So by using diamond dresser, you will dress the wheel so that you will bring this job axis concentric to the machine axis. That is what you will do in drawing. And then you will go into dress. Dressing is a process in which the wheel bond is removed. Here the wheel bond is removed, so it is opened out. The grids will be opened out. Wheel bond is removed to expose the abrasive grains. It is also done to provide space between the abrasive grains for the chips and flow and coolant flow. We need to dress the grinding wheels periodically as abrasive becomes. Dress the grinding wheels periodically. That means whenever it clogs or some every 10 pieces or 20 pieces, once you will go into dress that wheel, you will open out this abrasive periodically. So whenever it abrasive becomes blunt, then you will go into open it out by dressing. So this is the difference between truing and dressing of the grinding wheel. And in the this dressing also, there are different types of dressers are there. Stationary dressers are there, like that you must have seen single point diamond and or multi-point diamonds and also crusher diamonds. This is single point tool. Crushers are like this, crushers and diamond crush rolls and rotary dressers. These are the different types of dressers what we use. And the coolant nozzle design also is very, very critical in grinding, because this grinding, see, like that, if it's just splashing, in grinding zone, there will not be sufficient heat carrying capacity. So actually, this nozzle with high speed you have to impinge, so that this wheel should carry this along the surface should carry the coolant. Then only in grinding zone there will be sufficient cooling, and also it will carry the heat. Otherwise, this heat will be transferred to your component. Then it has got repercussions of component getting damaged due to cracks, or it may be new hardened zone, new tempered zone. Such type of things will happen. See, this is very nozzle design is very critical, and the speed of this also, that coolant, is also very critical. It actually forms air barrier, provided to ensure flow, grinding flow. Here we'll usually in nozzle top will give an air barrier, so that air will not go inside, only coolant will come. And this is G ratio. I think this is not this one. And which are all the factors which affects grinding? Already we discussed: machine tool, workpiece, coolant, what type of coolant system you are using, dressing, and grinding wheel, what type of wheel you are using. This is, and also you can change factors which influence the grinding process. One is changing the infeed. What type of infeed you will give, depth of feed you will give. That is one critical. And next is changing the workpiece speed. This workpiece speed also is very critical. And then changing the wheel surface speed. This wheel surface speed. These are all the grinding parameters I'm just telling. Changing wheel surface speed and changing the wheel diameter. If the small diameter, what happens? If big diameter you are grinding, then automatically this surface speed also will change. And dressing method. What type of dresser you are using? Rotary dresser or single point or multi point. These are all the things which influence the grinding, that whatever the quality of output that you are expecting. And usually, frequently, we get in grinding problems like grinding wheel hardness, like burn mark, or surface finish, low surface finish, and form loss. That means roundness and tightness. First few pieces will come, and subsequently you don't get consistency. So such type of troubleshooting comes. Then for that, what is the thing? Like grinding wheel, hardness and structure is important. Coolant nozzle, filtration, supply foaming, dressing speed ratio, direction of rotation, feeds and speeds, table rate, depth of cut, and wheel speed, fixture rigidity, and motion. These are the influencing factors for problem. For example, burning comes. What are all the causes for burning? With respect to, if you take coolant, up to 80% of the burning problem caused by inadequate coolant. Coolant is very important. So at right point, at grinding zone, sufficient coolant should be available, and velocity of that and like this coolant temperature and coolant concentration. Usually the 1:20 or 1:40 ratio. This also matters. So this is connected with coolant, and also wheel. For example, grid size too fine. Then what happens? It will not take the cut at all. More heat is generated, and you will get a burning mark. Structure not open enough. Open structure wheel should be there. And wheel too hard. It's acting very hard. Hardness. Abrasive not friable enough. That is type of abrasive what you are using. So this is connected to wheel. Dressing speed ratio between wheel and roll, and wrong direction of rotation. Dresser excessive worn out. If a dresser is worn out, again instead of opening out the wheel, it will blunt further. Then what happens? This will cause. So these are all some of the tips for uh, troubleshooting, like burning, and also feed and speed, more depth of cut. These are the influencing factors for burning. Similarly, if you take loss of form, roundness or straightness is going. What are all the things? Like wheel soft, structure open application, wheel out of balance. Balancing is very important. That's why whenever we are grinding in mass production, we are doing manufacturing, then form is very critical, like the roundness and straightness. Then we'll suggest dynamic balancing in addition to the static balancing. Similarly, dressing, machine, fixturing, feeds and speeds. So these are all some surface finish also. Whenever surface finish goes, this dressing is very critical here. speed ratio, wrong direction rotation, new diamond. Whenever new diamond, if you put initially, surface finish will be slightly high, but once it gets settled, then it will, after subsequent 2-3 pieces, you will start getting a good finish. So whenever loose particles, when are knocked off by dressing, if it comes in between this wheel and component, then also initially surface finish will affect. So this is connected with and also burning will happen. Sufficient coolant is not there, then happens. Corner retention. These are all some of the troubleshootings. So finally, any development in grinding. So there are different types of grinding. For example, ultra precision grinding, nano precision grinding. When we talk about less than 1 micron, and depending upon the surface quality and productivity. So you have to balance which one to use. Productivity also is important. At the same time, you have to achieve this stringent quality. One is ultra precision, rough, and finish, like that. So here, micro finishing, super finishing, film polishing, precision grinding. And this is rough grinding. Whenever high speed grinding, whenever you do rough grinding and a high volume of material is removed, your productivity is more, but your surface quality, what you achieve is less. Whereas ultra precision, your productivity is less, but surface quality achievement is more. So this is about in grinding, you have to balance where actually what is required. And one thing is important to see whenever we are talking about this accuracy and precision, the difference between accuracy and precision is very, very important. See here, low accuracy and low precision. Accuracy is not there, precision is also there. Here, it is low accuracy and high precision. See, precision. So spread is very, for example, you are aiming at diameter tolerance of about within 5 microns. If all are coming within 5 to 6 microns, then here it will come. But from X bar, if it is from the middle of the thing, if it is shifted, got shifted, then all has gone. This is only X bar mean shift. That if you can always correct very easily. Here spread is less, but it is not meeting your requirement. So this is high precision, but less accurate. And high accuracy and low precision. See here it is precision is not there, but accurate. Most of the things are coming in and around the center, but spread is more, variation is more. Here variation is also minimum and accuracy is also good. High accuracy and high precision. So in most of the time grinding, we aim for this. That is it. And finally, what we do, why we do this, this in grinding is this thing here, and also the finishing operation in auto industry, we will be doing mass production. So here productivity is very, very important. Even though you have to achieve that precision and accuracy, at the same time, you have to maintain productivity also. So here, how to improve productivity in grinding is a big subject, but I'm just giving a glimpse of it. One is it depends upon we are in grinding actual operation. We have got some limitations will be there, like process optimizations we can do to improve the quality. Whereas availability losses like setup time reduction, number of times changing the wheel, a number of times dressing, those things will any productivity improvement. There are 3 types of things. One is losses. That is, one is availability loss, and another is performance loss, another is quality loss. So to elaborate this, for example, 8 hours production, if you do, 8 hours means nearly about 420 minutes you'll get. Entire thing you don't get for grind. This one for the machine will not get for processing. So here you lose availability loss, like setup time, 1 hour setup time will be there, lunch time will be there, and changeover time, and also some you give some allowance for the operator for the rest time. Such things will go in availability. And performance loss. For example, cycle time is around 30 seconds. If he's grinding at 35 seconds, is in this one, then 5 seconds will be lost. That comes under process, that is performance loss. And then quality loss. If you produce 100 pieces, out of the 90 are okay, 10 are rejected. Then means the 10% is the loss for the quality. So finally, if you see here 10%, here 10%, here 10%, you'll lose about nearly the 30 to 40% of the productive. time productivity will lose. So here, like process in here, the QCO single minute exchange of time, these things will play a role in setup time. And in optimization, process integration, cycle time reduction, by tooling, improving the tools, you can improve the cycle time, you can reduce, and by automation you can reduce, so that you can increase the output here. That is the basic this one performance. And also here you can first pass yield improvement, reduction in scrap and rework. The percentage if you reduce, here quality losses you can reduce. Quality loss, performance loss, and availability loss. With all these things, you will get the productivity. So this is some of the examples of how we reduce the cycle time. I think I am running out of time. This one example here, surface rendering, we are doing here one phase at a time. Then we shifted to quick oscillation. So instead of entire table moving and grinding, we kept this table constant, and here we introduced a quick oscillation table. So from this we could reduce the cycle time from 24 seconds to 16 seconds. And further what we did is, instead of doing two surface rendering, here we brought two wheels we brought, so that component will be moved between these two wheels. So like this, we can improve from the cycle time from 24 seconds to 16, 16 to 14, and 12. I think with this, I'm just concluding. One is we understood what is the criticality of grinding, why grinding, and what are the applications of grinding, and how to select the specification of the grinding wheel, which are different applications, and how to optimize, and how to improve the product. These are all the things about in short, these things we have covered.